Welcome. Welcome to the last of the videos for Unit 3. This is on the projectile range formula. The projectile range formula is on the formula sheet already, and I believe it is 3.5 if I recall. Let's take a look here. There it is right there, 3.5. So hopefully that helps. You've seen it before a little bit. Um, it shouldn't be a surprise to you. This R right there is the range. This v sub ln is the launch velocity. Notice it's squared, multiplied by the sine of 2 times the launch angle. That's 2 theta right there, divided by the opposite of little g. Now, it's nice that there's an opposite there because, of course, then that would cancel out the negative in the negative 9.81 meters per second. And that would then give us a positive range, which, of course, you want, right? So that makes sense that your launcher is going to launch in front of the launcher and not behind the launcher, because really that's what that would mean if it was a negative answer. So we're not going to look at that. We're going to look back here at this as I try to explain how that works. So if I wanted to, I could go through and try to solve this without using the range formula. Here's what that would entail. I have to be able to use this initial vertical velocity to be able to find the time. So that would give me the time. So this would be my steps right here, right? So step 1 would be use the initial vertical velocity to find the time in the air. That should be pretty easy. As you might imagine, the higher the initial vertical velocity is going to be, the farther up in the air it's going to go, and therefore the longer it's going to take as it goes through its path through the air. And so these two, the vertical velocity and the time, are very strongly related together. In fact, this one determines that. So that would be my first step. My second step would be to use the horizontal velocity times the time to figure out the range. So when you look at it like that, it doesn't sound like there's a lot of steps in there. But in reality, you have to be able to calculate this, which takes a step. You have to be able to calculate that, which takes a step. You then have to be able to calculate this using the the master motion equation, and so on. And so really, even though there's only 2 major steps, each step itself has quite a few steps, sub-steps, if you will, involved in it. And so it's much easier just to take into account the fact that we can collapse all of those steps down into one formula. So this one formula looks like this: delta x, which is the same thing as saying capital R, right? So the range right there is capital R. It's not the capital R for a resultant like we sometimes use. In this case, it's the range. So don't get confused by that. You may actually see somebody else use a capital D as well. That's the distance that the projectile moves. It doesn't really matter. The main goal is, where do you want to put your target, right? Where is the projectile going to hit when it gets back down to that same level again? And so it doesn't really matter what you call it, but all of those things would work. And that's going to be equal to the launch velocity squared multiplied by the sine of 2 times the angle, launch angle right there. Don't fall into the trap of saying that this is 20, because it's not. It's 2 times the launch angle. And then all of that divided by the opposite of little g right there. Now, all of these things, this launch velocity squared and the sine of 2 times the angle, all come from the fact that this has many, many steps in it. And so if we're going to use all those steps to try to figure this out, we could do it algebraically and then just solve so that we have one small formula. And that's really what I did for you to come up with this range formula. Some areas where people have troubles. Number 1, they forget the fact that the launch velocity right here is squared. Okay. Number 2, they forget the fact that this is the launch velocity itself and not either the vertical or the horizontal components. So what I'm really talking about is this guy right here. What is that? That one. That velocity's magnitude goes in right here. And so we have to be careful about that. That's squared. And then we multiply it by the sine of 2 times the angle. Again, this is an area where people have confusion. 2 times the angle right there. It comes from the fact that when we collapse this down, we end up with this trigonometric identity that says 2 times the sine of theta times the cosine of theta, which then becomes 2 times the, the sine of 2 theta. Those two things are equivalent, and so we have substituted in for that. And then last but not least, people forget that they have to take the negative of the, or the opposite of the value for little g right there. Again, it wouldn't make a lot of sense if we plugged all this in and got a negative number for our range, because that would mean basically that the projectile was launched and then went backwards. And that doesn't make a lot of sense. So please make sure that you're gut checking this stuff as you're doing it. Again, this shows this is for an ideal projectile, and it assumes that we have a perfectly parabolic trajectory, which, as it says here, you need to make sure is symmetric across that vertical line right there. If you don't have that, if you're outside and you're launching an actual projectile, then this range formula is going to give you the ideal range, and it's important to remember that the ideal range is always going to be greater than the actual range because of air resistance. So what does that look like? Well, if I have a, let's say an XY plot right here, so this is the height, and this is the distance away from the launcher, and we put the launcher right here at the origin. I'm going to try to draw as best I can here. In blue, an ideal projectile would look something like this. Ooh, getting kind of fuzzy there at the end. And then a real projectile would look something more like this, where you get, it doesn't go quite as high because air resistance is slowing it down, and then it ends up really slowing down quite a bit and coming almost straight down as it gets closer to the end of its path. And so this is the air resistance path, and the other one there is the ideal. So we try to stay in the ideal because it has this nice parabolic shape, and it's easy to deal with mathematically. But quite frankly, every projectile we'll ever have to actually deal with is subject to air resistance, and so ends up being like this. So it has this kind of weird cutoff, drop off at the back here. So we have to take that into account. Okay, if you have any questions, go ahead and let me know. Otherwise, you should be able to apply this at this point. Don't forget we have that test coming up, so make sure you know and understand, can be able to use this, because there will be problems on the test for it. Thanks. Have a good day.